Hello, everyone. Welcome back to our seminar series on fractional calculus and related topics. Today's speaker is Professor Katarzyna Gorska. She is full professor at the Theoretical Physics Division of the Institute of Nuclear Physics of the Polish Academy of Sciences in Krakow, Poland. Graduated from the Nicolaus Copernicus University in Toruń, she earned her PhD in theoretical physics there and completed postdoctoral fellowships at the Sorbonne University, campus Paris 6, and the University of Sao Paulo. She served as a visiting scientist at research centers and universities in Europe, France, Italy, South and North America, Brazil, USA, Canada. She has authored or co-authored over 60 scientific publications. Her main research interests include transport phenomena, diffusion, heat transfer, dielectric relaxation, evolutionary equations, fractional calculus, stable distributions in probability and physics, integral transformations, umbral calculus, and special functions. Her other scientific interest, sometimes treated as a hobby, is foundations of quantum mechanics, in particular, the mathematical theory of coherent states. And today, she will give a talk for us about integral decomposition method and the Efros theorem. Please, the floor is yours.
Thank you very much for introduction. Very nice. So here is the title of my presentation, and as you see, I will be talking about some methods of solving the integral differential equation type of anomalous diffusion equation. And I am from Krakow, from Institute of Nuclear Physics, Polish Academy of Sciences. Here is the logo of our institute. Outline of my seminar. I will start with description of the Fokker-Planck equation with memory functions, with the integral kernels, and here, as you know, there is very important subjects related to them. It's a Sony equation and Sony pair, and as we know, the Fokker-Planck equation is a equation defined in time and space, but very similar equations defined only in time regime is dielectric relaxations equations. So I will mention about them. And the second subject is we want to find the solution of Fokker-Planck equations. And for them, we will use integral decomposition method, which under some assumptions goes to the subordination method. And I am very interested in tricky methods of solving some equations, and I will use the Efros theorem. Then, as an example, mainly I will introduce the generalized Cattaneo-Vernotte equations, and I will explain the difference between the telegrapher and Cattaneo-Vernotte equations. They look the same, but the interpretation from physical point of view is different. And here is an example where we can give the at least two kinds of subordination, and both of them they are correct. And another example is the Doppler effect frequency shift related with these telegrapher equations here. Next, I will say something about Havriliak-Negami relaxation and about evolution operator approach. So we will start with generalized Fokker-Planck equations. It looks like that. So what we have here is defined for simplicity in t time, which is non-linear, and x here, which is on the real line. O is the linear operator, and which contains the information about the memory effect for physicists, and such operator LFP is a Fokker-Planck operator which is independent on time and depends only on the x space. So we can write it in such a form. Here is the integral representation of this operator, linear operator O. So we have the integral from 0 to t kernel and act on the Laplace transform acting on P. But such equation in the literature, we don't find it. We find such type equation on another type equation. Here is related with master equation and its derivative over time. And we have one kind of integral kernel. And when we calculate when we integrate these equations, we obtain such a form. Here is the initial condition, and we can also find in the literature another equation, which it's also called the generalized Fokker-Planck equations. Here we have another kind of integral kernel, okay, on t minus xi, and Fokker-Planck operator. And many people considered such two types of equations. And here is just I just give the names like Maynard, Sokołow, Czechkin, Koczubej, Tomowski, Sandev, Metzler, and so on. Many of them. So I will just insert this name, give this name, but you can find a lot of papers about them. The question is, we have this equation is written in two forms. In the literature, you can find it in these two forms. And the first question is, if the solutions what we obtained from these equations are, when the solution obtained from these equations, these functions p, are the same. And we can answer on that equations. And they are the same, they are equivalent if the integral kernel m and k satisfied the Sonin equation. Sonin equation is written here. So it is a Laplace convolution of the kernel m and k, which is equal to 1. After taking the Laplace transform, of course, it can be written like that we have hat means the Laplace transform. We have m function hat m times hat k is equal 1 over r and 1 over s. And also about the Sonin equations, many people wrote it, and Sonin who introduced it, and also Koczubej, Hanega, Luczko, we wrote. And remark 2 is related when we obtained the first equation previously mentioned, if the Laplace transform of kernel O is given like that. And as you see, there is a problem with at 0, at t equals to 0. Why? Because it is the Laplace transform form, and when we want to back to the time space, time is always related with the Laplace transform, because it's defined on the positive. In classical mechanics, it's defined on the positive semi-axis. And here will be the derivative. And as we know that the inverse Laplace transform of such formula is related with the derivative and the behavior of such functions at 0. Okay, so except the Sonin equation, you can define the Sonin pair. And the functions m and k, our kernel, they are locally integrable. And if they are locally integrable and satisfied the Sonin equations, we called them Sonin pair. And so it means that the kernel m is associated with the function Sonin functions k and vice versa. Locally integrable, it means that at 0 exists the integrable singularity at 0. And if M is regular, then K is distribution. I will give the example of that, but in the next slide. Example. The first example, which was given by the Sonin in 1884, it's like that. It's related with the Bessel functions, the Bessel functions of the first kind, and the modified Bessel functions. And these two kernels behaved in such a way. So we have the negative parts, yeah, and the positive parts. And what else? The kernel K is presented here. Here we have the singularity at 0, and it goes also to infinity, where the t, whether the argument goes to infinity. So we can use such kernels to solve the integral differential equations. Nevertheless, we don't want it. We want to have such a kernel who at the beginning they are infinity and go smoothly to 0. Oh, sorry. Such behavior are satisfied by these two functions m and k. It's proportional to t to the power alpha minus 1 and t to the power minus alpha, where alpha is from 0 to 1. And both of them, they are non-negative functions and behave in such a way that at the beginning, for t equals to 0, they are goes to infinity, and such singularity is integrable and smoothly goes to 0. And the question is why when we meet these such kernels, obviously the answer is that one is related with the fractional integral and another, this one is related with fractional integral, and this one is related with fractional derivative. Usually Caputo, fractional derivative in Caputo sense, but also in Riemann-Liouville. So another example, we have here the Luczko class, and Professor Luczko introduced this class. What it means that he separate from our integral kernel, he separate the singularities, and the singularities all the time has the form of exponent expression. So here we have the singularity and the regular behavior, such a regular that we can present it as a Taylor, as a series, where here we have the coefficient AR times TR. Alpha is from 0 to 1, and also the kernel K can be also presented in such a way that we extract the singularity. Here is t to the power minus alpha. Of course, these coefficients R and BR satisfy such relations, and there is many fractional derivatives which we can use. Belongs to the integral kernel belongs to the Luczko class, but there is a one maybe not one, but exception. It is the distributed order integral kernel. They are the pair which we have the integral from 0 to 1 t to the power alpha minus 1 divided by gamma function on alpha, where we integrate over alpha. And it is related with Volterra function. And here we have the Sonin pair. It's a K functions. It's given by the integral exponential integral, I think something like that. So here is the distributed order integral kernel. It's something which do not belongs to Ludko subclass. And I will call it some counterexample that we have the functions which is regular at t equals to 0. It is the exponential function. And as we see, its Sonin pair is given by the distribution functions. It's delta Dirac distribution. Okay, and of course, Sonin pair before the Luchko was introduced by the Kochubey, and here is the Kochubey approach to solving the equations of anomalous diffusion type. And he said that the solution exists, unique solution exists, if the integral kernel are Sonin functions. Here is the definition of the Sonin functions, and satisfy such limits. And this limit, it means that here is, this limit means that at 0, the functions goes to infinity, and at s equal to infinity, it goes to 0. So the behavior is like that. So it goes smoothly. And physicists called such a behavior as the fading memory. And as I said, below is definition of Stieltjes functions. We have the functions a and b, and usually we take the parameter a and b, and usually we take that it is 0. Why? Because physicists don't like to touch the point 0. Okay, when we say about the Sonin pair and fractional calculus, it is important to mention about the first and second fundamental theorem. But before, we should note that we can introduce two kinds of integral operator. One is generalized integral operator, which is defined here. And another is generalized derivative, which is defined here. And we have here this generalized derivative, two versions. One is up and another is down. And the difference between them is only the position. When we look at the difference is that the position of the derivative. It should be derivative over t. Sorry for the mistake, because it was copy-paste. Here is derivative over t and the derivative over xi. And that version is related, we can say that it is a la Riemann-Liouville derivative, and this is a la Caputo derivative. And this one is just regularized version of Riemann-Liouville derivative. Physicists like that version. And we use that version. So here is the first fundamental theorem. So it means that when we act the generalized derivative on generalized integral on functions f, all the time we obtained that it is the functions f. But when we act integral, generalized integral derivative on generalized derivative, defined like here, we obtained also f on t. But when we act on that, it is the regularization related with behavior of functions at 0. Okay, so in conclusion, we had two kinds of Fokker-Planck equations, which are written in such a form, on such or another form, and they are equivalent if the results are equivalent if the m and chi integral kernel memory functions called memory functions satisfied Arsonin pair. And the question is, in which way we can find these functions, these memory functions? And one of the answer, I think that the simplest one, is just by measuring the mean square displacement. When we take the Fokker-Planck equations, which is related to the second derivative, fundamental solution is related with Gaussian. So we know that the odd moments, like mean value, are equal to 0, but the only even moments exist, and the second moment is related with in such a way with memory kernel M. Of course, when we use the Sony equation, we can find the relation with the memory function K. So here is for the Fokker-Planck equations, and Fokker-Planck equation is defined in X and T. But when we cancel X, we obtained only the dependence on time. And instead of this Laplace operator here, we have the constant factor B. And also this constant factor can be found from experiment. And in that case, we have the dielectric relaxation. And the equations are very similar. Look at that, they are very, very similar for that one, here and here, just we don't have the X dependent. X dependent. And what is these functions n on T? N on T, it's called the relaxation functions. So we have here the relaxation functions and the memory functions M and K, and the parameter P. And all of them can be found also from the experiment, and because they are related with with spectral functions. Spectral functions is related with permittivity, but I will not talk about that. And here is the spectral functions is related like that. I it's a complex number. So it is 1 minus I omega. Omega is frequency. In the Laplace space, it is relaxation functions minus I omega. When we take for example, this Laplace transform of that equations, we obtained here. And from both of these equations, we obtained relation between the spectral functions and the memory functions. Okay, so we have such equations like that, and we want to solve them. So to solve them, we can use the integral decomposition method. Integral decomposition method is nothing strange. When we have the smooth functions, all the time we can present it as integration of the product of two functions, two smooth functions. So here we have the functions h and f. And first remark is that this procedure is not unique. And we can proceed in two ways. First way related in that direction is that we can, if we know the functions p, we can find many combinations of functions h and f whose integration gives these functions p. But also we can proceed in another way. And here it is this another way. When we know the functions p and the functions h, there is only one smooth functions who can be put here, can be given here. So so usually this is what I've observed. The people are followed that way, that they know the functions P, they know the functions H, and try to find the functions F. Okay, and here we can have the relations with the subordination method. And if we want to have the probabilistic interpretations, we interpreted these functions H and F as a probability density of the parent and leading process. Here is the probability density of parent and the leading process. And Xi is interpreted as the operational internal time. Previously, it was just the integral variable. But to have the probability interpretations, we need to assume at least two assumptions. First is that our functions are normalized. It means this one. And the second, they are non-negative. Probability is non-negative all the time. And the third assumptions which we add is that these functions have infinitely divisible functions. And I found that in Sokolov in 2002 and Szczerkin and Sokolov 2021 in their paper, they wrote that we can consider, with respect to F, we can consider the safe and dangerous probability density functions F. So what it means? It means that if the functions, if the functions have satisfied all of these conditions, three conditions, we have the safe PDF, and it subordinates the H functions. But if one of these conditions are not satisfied, we have the dangerous PDF. So observe that here we assume that H functions is just the probability density function, so it's normalized and non-negative, and only the functions F can be dangerous. And later I will show you the example that we can also find the example where the functions F is okay, satisfied all of these conditions, but functions H not. Okay, how to show it that it is non-negative functions? Of course, we are using the Bernstein theorem. Bernstein theorem in the unique way connect the completely monotone functions here with the non-negative functions by the Laplace transform. So here we have the completely monotone functions and the non-negative functions. And this is one of the reasons why the physicists like the completely monotone function. Okay. We will also use another functions with completely monotonicity of the functions. They are related also Bernstein function, complete Bernstein function, special Bernstein function, logarithmic Bernstein function, logarithmic completely monotone function, and so on and so on. So what it is the complete monotonic function? It means that all derivatives, it is real functions, first of all, and all derivatives exist and alternate. And here we have the properties which are very often used, and the product of two completely monotone functions are also completely monotone. The composition of completely monotone functions as the Bernstein function is another completely monotone function. And here is the definition of Bernstein function. The difference is that that the functions is Bernstein functions is positive, is real and non-negative, let's say, and their derivative alternate, so it is completely monotone functions. Here we have the completely Bernstein functions, and such functions is the Laplace transform of completely monotone functions. So it is the inverse of the Stieltjes functions. And of course, the completely Bernstein functions is the subclass of Bernstein functions, and so on. So here was, in this way, we can explain using that functions as the Bernstein theorem, we can explain the non-negativity. And what we have proved that that our solutions are normalized, our functions are normalized and infinitely divisible. And both of these features can be proved when our functions f in the Laplace, after the Laplace transform has such a form. That here we have k on s and exponential of s, k on s. Or here is a -1n, inverse of m, algebraic inverse, let's say. And here is the exponential xi and divided by n on s. And these two functions are memory functions and they are shown in pair. They are Stieltjes functions. And if such, it means that if they are Stieltjes functions, it means that the algebraic inverse of m, which is equal as this one, is complete Bernstein functions. And we call it the Laplace exponent. So when we have such a form, we immediately see that this function's f is normalized because it's just the derivative. So it will be inverse Laplace transform of 1 over s, and it is 1. And infinitely divisible, we can prove in two ways. First way, by using the logarithmic complete monotonicity of the functions. It means that the minus derivative of logarithm of functions L is completely monotone functions. And it can be proved that such form, when k is Stieltjes functions, is this logarithmically complete monotonic function. And in this book, Bernstein functions, we can find the theorem 5.11 that if the functions is this LCMF, then it is the infinitely divisible functions. So it is one way. The proof can be found in my paper published in this year. And another way is just by using the inverse Laplace transform properties. And we can find, by using that properties, we can find such a relation where we have here the functions f and the functions u, g, which is defined like that. So here is the relations between the inverse and the direct subordinator. And why we are interested in this? Because of such sentence founded in Bernstein functions on that book. Why? Because it's if we have the functions j here, they satisfy such relations. So and there is written that the infinitely divisible functions satisfy the semi-group composition property. Because of this, and I believe we believe, my group believe, that it is related with composition causal law. Does this, and here the semi-group composition property are for Levy-stable distribution. Psi is Levy, it's two-argument Levy-stable distribution. This is very known, very well known. Levy wrote about it, and here is the Mittag-Leffler functions, which also satisfied such properties. And alpha is from 0 to 1, and here is also alpha from 0 to 1. Okay, so we have the anomalous diffusion equations, and we want to solve it. When we take the Laplace Fourier transform of the anomalous diffusion equations, we obtain the algebraic equations, and from this algebraic equation we can solve it and found the functions p, which is written in such a form, that one or that. And the memory functions n and chi are Sonic-Peck. But we want to calculate the inverse Laplace and Fourier transform such that we want to have the pay function on x and t. And what we can do? It is difficult to solve such equation, formula, the inverse such formula, and we can use the I've called it X parametrization, which based on using such formula 1 over a can be presented as the integral from 0 to infinity exponential functions minus a, like that, u du. So here I've presented this denominator as an exponent. Okay, stay here. And here, when I take the exponential functions of the denominator, I will add the sign, and one part related with that it's here, and another is here. So of course I've shared the dependence on x and t. Kappa is related with Fourier transform like tilde, and S, like hat, is related with the Laplace transform. S is the Laplace coordinates, and K is Fourier coordinates. So I can calculate only we can calculate only the Fourier transform of that part and Laplace transform of that part. And what we obtain when we take the Fourier transform of that part, we obtained the Gaussian. It looks like that. And here we have the Gaussian on x and xi. So it is the Gauss functions where we have n and xi. And here we have the inverse Laplace transform defined like that. It should be set as. Okay, but we can also, in the literature, we can also find the diffusion wave equation. What is the difference? The difference is that here we have the second derivative. We are blurring the second derivative of time. Psi is interpreted as a time. We have different memory kernel. And because of the second derivative, we have the two initial conditions. Of course, we are taking the fundamental initial conditions. It is not necessary, but for simplicity, we are taking, as previously, fundamental initial conditions mean that the solution is equal to the delta Dirac distribution and its derivative is equal to 0. So we can calculate the Laplace Fourier transform, and solve these algebraic equations, which appear, and our solution has such a form. It is Fourier tilde Laplace version of our solution. And of course, we can use also the exponential parameterization. So we can present the denominator in such a form, like previously. But here we have the functions g and psi s, and it looks like that. And when we think a little bit, it's turned out that this parameterization does not always work. Why? When we take that eta on S is equal 1, it means that we should calculate the inverse Laplace transform on S squared. Yeah, and such inverse Laplace transform does not exist. And also where we have the power law memory functions, eta is S to the power beta minus 2, where beta is from 1 to. It also means that it's not the Bernstein functions, and it means that that Laplace transform doesn't exist. And here is the beautiful, it was written in the beautiful paper of Trieste, Sandev, Zhiborat Tomowski, John Dubbeldam, Alexei Chechkin. Here, generalized diffusion wave equation. And in that paper, they proposed such solution, where instead of taking the memory functions, you should take the square root of memory functions here. So they proposed such solution, and this solution can be easily obtained when we take the partial fractional decomposition, and after that exponential parameterization. Our solution is given like that, is n eta s square eta plus k, and first we are making the partial fractional decomposition of denominator, which looks like that, and after that we calculate the exponential parameterization. So we obtain such a result, and we separate the form which belongs to the Fourier space and the Laplace space. Here, of course, it's an inverse Fourier transform at exponent plus minus I psi kappa. So it is related with delta distribution. It should be K. X, and the inverse Laplace transform. And when we calculated this, we obtain such formula. And both of these methods can be found in the Efros theorem. And what it is, the Efros theorem? Efros theorem is some generalization of Laplace composition. We have here two functions, J and Q, and the Laplace transform of the functions H exists, and the Laplace transform of another functions G, it's given like that. So it is the J functions exponential function minus psi QS. So then the theorem says that if our solution has such a form, it can present like that. So here you see that we have integral from 0 to infinity, and it is the integral decomposition. So where we invert it, we have the integral decompositions is given like that. Here is written that in the inverse Laplace transform. And we have here also two examples. First example, we have the diffusion heat equations. and whose fundamental solutions is a Gaussian. So that Gaussian in the Laplace Fourier space means this. And thanks to the Efros theorem, we can present it as another Gaussian, but from kappa and psi. And here is the delta functions. And what we have here? We have here the Gaussian functions related with the Gaussian functions. Gaussian functions is the solution of parabolic equation. So it means that parabolic equation is related with infinite propagation speed. So we have equation with infinite propagation speed, equation with infinite propagation speed, and physically it is okay. But in another case, also by using the Efros theorem, we can present such a Gaussian as a solution of a wave equation and such a functions. This inverse Laplace transform reads like that. And what we have here? We have the solution of parabolic equation and the solution of hyperbolic equation. So we have the mixture of, we want to obtain the solution of an equation with infinite propagation speed, and from the solution of the equation, hyperbolic equation, we have which has the finite propagation speed. So for physicists, it is impossible to build something with infinite propagation speed by using something which have the finite propagation speed. So this is the reason why I wrote the counter example. And another example is the generalized Cattaneo-Vernotte equation. These equations looks like here, and we have the second derivative, time derivative, the first time derivative, and x, and the functions which the memory functions eta and gamma. Because here is the second time derivatives, we have we are choosing the fundamental initial conditions like that, and we assume that our boundary conditions, that solution vanished at plus minus infinity. And memory functions are related by the Laplace convolution. And it's given like that. So in Fourier space, it means that eta, in Laplace space, it means that the Laplace transform of eta is the Laplace transform of gamma to the power 2. Okay, and here is that when we take that eta and gamma are given by the delta distribution, we obtain the telegrapher or Cattaneo-Vernotte equations. Both equations looks the same, but physically their interpretation are different. First, when we look at on the telegrapher equations, is describe the voltage current along the electric transmission line. And the parameters eta and A are related with the electromagnetic quantities that characterize the line. And it is capacitance, resistance, inductance. First difference, the second is the initial conditions. When we say telegrapher, it means that first initial conditions is a real, it can be real function on x, and the second is also it means that derivative of u is also the real functions. So what it means? It means also that u on xt can change the sign. It can be positive and also negative. But when we say Cattaneo-Vernotte equation, that equation was introduced by Cattaneo and Vernotte for describing the heat transport with finite propagation speed a, and tau is the time parameter. And this equation can be derived from the continuity equation and the modified Fourier heat conduction law is given like that, and such a way was propagated and developed in the paper written by Compte and Metzler. And also here the initial conditions are like that the first initial condition is non-negative and the second condition is equal to 0. And our solution U must be non-negative functions. And this is very strong assumption. Why it is non-negative? Because we are searching the probability density. And the solution looks like that. So it is very, very nice solutions. We can solve it. And the first solution was given by the Morse and Fischbach. In their book, we can find this solution. And for fundamental initial conditions, it's written like that. So here we have two Dirac distribution, the Bessel functions 0 and 1. And because of this theta, which is Heaviside step functions, we have the wavefront. So what it means? It means that because wavefront is in the wave language, that our solution is not 0 only on the finite region. And this dashed line here and here is just introduced by me to show it that it is the non-zero solution on the finite region. Gosh, yeah. Okay, and what it is that we can also consider the limits, and these limits is obvious, but that one is just when we are very close to the 0. So it's very difficult to find the difference between the solution of Cattaneo-Vernotte equation and the diffusion heat equations, and where we are very close to the to this line x plus minus 80, we can solve it also by using the wave behavior. Okay, so we can have for the generalized Cattaneo-Vernotte equation by using the Efros theorem, we can have to subordination. And first, we can subordinate the Gaussian normal distribution, and here the functions f is defined like that. So the Laplace transform is written here. We have the gamma, ma on s functions, and square root. And we want to call it subordination, so it should be non-negative and infinitely divisible and normalized. Normalized is for sure, because we can present it as a derivative over xi, but non-negative and infinitely divisible, where these functions, memory functions, gamma s is the power low functions from alpha to 0 to 1. The non-negativity and infinitely divisibility is satisfied only for alpha from 0 to 1. But we can also follow the second one of the second kind of subordination, and we can subordinate the solution of the Cattaneo-Vernotte equation, and here use such functions whose Laplace transform is given to like that. And when we take the power law functions as a memory functions, this is always positive, non-negative, and infinitely divisible from alpha to 0 to 1. So it is really good. But and these functions Cattaneo-Vernotte is related with telegraph process, and it's also the probability density of the telegraph process. And that the second subordinations allow us to show if the solution is defined on is non-zero on the finite region R0, and it is defined on the finite. It is non-zero on the finite region if this memory kernel contains the delta Dirac distribution. It means that the second derivative exists. So it means also that it looks like the wave equations. With wave equations, it's related with Doppler effect. So the Doppler effect, what we need all of us knows the Doppler effect, where we have the observer and the sources. And the sources move in the way to observer. We observe the high frequency and the voice is much louder. And where they meet us, there starts to be quiet, and we observe the low frequency. And it is called the Doppler effect in short. So what we need the source. Source is given here. It is the complex functions. And we consider the external pod weight source, which pulsate with frequency omega and move with velocity v. We add for that equations and we can solve it. So here it is the equation, that equation without memory is written like that. And it is not probability because it's an exponential, because it's a complex function, it's not zero. And here it is the probability density. And for example, it looks like that. And when we see, so here is that our external source didn't move and here start moving. So when we see this green line and the blue line, because it's most visible, that here we see that line is much shorter than this one. And also the same behavior is here. Observe that our caps start to move on the right. Okay, because I do not have a lot of time, because it's almost 4. Here is an example with the dielectric relaxation. And also we can find in the relaxation, dielectric relaxation, the kind of Havriliak-Negami, whose spectral functions is given like that. Here we have alpha and beta, and there should be from 0 to 1. And we can find the two kinds of subordination. One is we subordinate the Debye relaxation and another Cole-Davidson relaxation, but this is only example. And Arran, are you there?
Yes.
Okay, can I 5-7 minutes more?
Sure, yeah. We are flexible about time. Just go ahead.
Okay, so here, because I would like to mention about the evolution operator approach, and Emilia Baszlakova wrote a lot of things about it. And they are very inspiring, because when we look at on Wider book, the heat equations, and we are searching this book, we found that we have such equation, and it is the diffusion wave equations or Fokker-Planck equation, and we can solve it by using the evolution operator. And there is written that here it is the solution by evolution operator, which is written like that. And it is the exponential functions on P, and there is a sum operator, which is the Fokker-Planck operator, acts on the initial conditions. Also, in such a book, a vector valuate Laplace transform and Cauchy problem, we have the the wave equations. And we can also find their solution by using the evolution operator method. And it is presented like that. We have the evolution operator acting on the initial conditions. And this operator, evolution operator, is related with cosine functions acting on the derivative on x. Also, what we can find in 2012, when I was a postdoc, I wrote the paper when we have the anomalous diffusion equation with fractional derivative of Caputo sense. And we solved this equation, but also using the evolution operator. It is like that. And here we have the functions O, FO, F0. And these functions F0 is related with Levi stable distribution. And in Emilia Bashlakova, in one of the papers, because Emilia wrote a lot of papers, here you can also find that they consider the Caputo derivative, but the order 2 beta. So it has that from 0 to 2. The solution where they cross from 1 to 2, this one, evolution operator acting on the initial conditions. And it looks, the operator looks like that. Sorry. So here you have the same functions, but for beta 2 instead of alpha, and initial conditions. So my question was, by using the Efros theorem, it seems that it is not necessary to consider only the fractional derivative on Caputo sense, but we can consider the generalized derivative. And here is for the generalized Fokker-Planck derivative. So we can present it as a Gauss functions and some functions f on chi, which is defined like that, like in Efros theorem, which acts on the such evolution operator, acts on the initial conditions. Such one act on the initial conditions, and also we can consider the generalized diffusion wave of wave equations, where we have also the memory kernel here. The solution by using the Efros theorem can be present like that when this functions g is given by the square root, and we can present it on as the action of the evolution operator on the initial conditions, which is written like this evolution operator is given like that. And the solution which we obtained is correct also. It's this what was obtained by the Trieste, Sandev, and Shivarat-Tomovsky. By using the Fourier transform method, I obtained such solution in 2025. But I feel that there will be something more. And this is the end. And here is the literature, which I used. Just that. Okay, thank you. Okay, 6 minutes.
Thank you very much for the presentation. Do we have any questions or comments from the others? Yes, Yuri.
So, Katarzyna, thank you very much for a very interesting presentation. And I am very glad to know that the theory of the integrals and derivatives with the Sonin kernels is actively applied in physics to different kind of problems. However, I have a small remark regarding the terms that you used on the slide number 6. Can you go to the slide
yes.
number 6?
Okay. Yeah.
Yeah. You called this class of Sonin kernels with my name.
Yeah.
Thank you very much. But indeed, it's not correct. Yeah,
Yeah.
because this class of kernels was introduced already in the original paper by Sonin. So it's
this
Sonin class of kernels.
Thank you.
Yeah, in one of my recent publications, I introduced a generalization of this class, namely Sonin kernels in a similar form, but with the functions M1 and K1 in terms of some series with the fractional exponents. So it's a generalization of this Sonin class. And of course you are allowed to call this new class with my name, but not this one. I mean, look, in the representations of the kernels M of t and K of t, we have a product of these two power law functions with power law series with integer exponents. Yeah. It's possible to generalize this class and introduce similar representations, however, with the power law series with fractional exponents.
Okay, so
it's a
it means,
generalization of this class.
So it means that the M1 and MK1, they are series of, you have some coefficient and the T is to the power some alpha R.
Yes, yes, yeah.
Interesting.
T to the power beta, yeah. So we can replace T in the formulas for M1 and K1 with a power law function like lambda multiplied by T to the power beta. Yeah, and derive conditions for these functions being Sonin kernels.
Okay, so and I found the information in your recent papers.
Yes, yeah. The paper has the title symmetrical, something like symmetrical Sonin kernels. Yeah, something like this. It's a more or less recent paper. However, these formulas for the Sonin kernels were introduced already in the original paper by Sonin. I can send you the paper because it's not so easy to find this original paper by Sonin.
Yeah. Thank you.
Okay.
So sorry for asking the question by me, Yuri. I wrote here the distribution integral kernel. And what is your feeling? Because my feeling is it does not belong to that class. Is it true or not? Because for me it's very interesting.
Well, I think you are right. You are right. This form of the Sonin kernels is sufficient of course condition, but not necessary. Of course, there exist some kernels that cannot be represented in this form. By the way, there is a paper written many years ago by Boris Rubin, who is a people of Stefan Samko. And in this paper, written in Russian, I also can send you this paper. Maybe something like 30 years ago already. Rubin introduced a class of Sonin kernels with the power logarithmic asymptotics at the origin.
Okay.
So as you see, these kernels M and K in this form, they have power law, pure power law asymptotics at the origin. And Rubin introduced a class of kernels with power logarithmic asymptotics. And evidently, they cannot be represented in this form, but still they are Sonin kernels. Also very interesting.
Okay, so please send. Yeah. Andrzej knows Russian. He can read in Russian, so it is okay.
Yeah. So I mean, the Sonin kernels built a very big set of functions, and of course they don't need to have power law asymptotics at the origin. It's the simplest form.
Yeah.
But several other types of asymptotical behavior at the origin are also possible. For example, power logarithmic asymptotics.
Okay.
Okay, thank you. Thank you again for your interesting presentation.
Thank you. If I may add something briefly to this discussion of the generalized version of the kernels on this slide, I think one of my papers may also be relevant to this on the so-called general analytic kernels, which I defined using t to the power of alpha times an analytic function of t to the power beta. So it would be, again, generalizing this with fractional powers inside the series. Okay. I did not use the terminology of Sonin kernels because I was not aware of it at that time, but we did find a condition for the two, like the fractional integral and the fractional derivative, to be properly inverses of each other. So it might be equivalent or at least related. There is also the work of Reiner from 2005 that also introduced fractional integral operators of the same form, but I don't remember if that paper also did fractional derivatives. So maybe there was no Sonin type condition there. But I was coming at it from the viewpoint of let's have an analytic function so that we can describe so that we can have a series formula for the fractional operators. Whereas I think you are coming more from the point of view of starting with the Sonin condition and then putting analyticity into it. Whereas I was more starting from analyticity and then finding essentially a Sonin condition, but maybe it's the same thing in the end.
Yeah.
Any other questions, comments from anyone? You don't have to raise a hand. You can simply unmute and ask or say if you want to say anything.
Question, please. Question.
Yes.
Yes, thank you very much. Can you open the sixth remark?
What was it? 3, 4, 5. What was it?
There.
Oh, yeah, yes.
Yeah. In the here, 1 divided this tau, 1 divided tau is a coefficient, a constant coefficient or variable coefficient?
It's a parameter. It's related with the time. Why? Because it has. Well, what kind of interpretation do you want? Telegraph or Cattaneo-Vernotte? Because it's a little different. Well, because when you follow the telegraph equation, it is the combination of the capacitance, resistance, and inductance. It is the parameter and your measure. And here, when you follow the Cattaneo-Vernotte equation, it's related with modified Fourier heat law here. And you are assuming that its time lag, it's very small, such that you can use the Taylor expansion of this current J, and
Yeah, yeah.
just fix the first and the second term.
Thank you very much.
So it depends on the interpretation which you are using.
Thank you.
Okay, thank you. Any other questions or comments? If not, then once again, we thank the speaker and